There are more stars in the observable universe than grains of sand on every beach on Earth. Many of those stars are billions of years older than our Sun. Around a great number of them, planets orbit in the quiet dark. If even a small fraction of those worlds gave rise to life, and if even a fraction of that life found its way toward complexity and intelligence, the galaxy should be full by now. We should be hearing something. Signals drifting across the void. Evidence of civilizations older than our continents. And yet, when we turn our instruments toward the sky and listen as carefully as we know how, we hear nothing. Just the soft background hiss of the universe itself. We are going to sit with that silence and explore what it might mean. You're listening to Sleepy Time Universe, calm science for curious minds seeking rest. Tonight's subject is the Fermi Paradox, one of the most quietly profound questions in all of science. Not a question that demands an urgent answer, but one that rewards slow and patient thinking. We'll move through it gently, giving each idea the space it deserves. We'll look at the mathematics of probability, the strange weight of cosmic time, the proposed explanations that scientists and philosophers have offered over the decades, and what the silence of the universe might ultimately tell us about our own remarkable existence here on this small, pale planet. Get comfortable. There is no hurry. The universe has been quiet for a very long time, and tonight we are simply going to listen along with it. Chapter 1. The question that started it all. It began, as many great scientific moments do, not in a laboratory or an observatory, but over lunch. The year was 1950. A group of physicists were walking together at Los Alamos National Laboratory in New Mexico, a place that had spent the previous decade at the center of some of the most consequential science in human history. The men working there had helped reshape the world in ways that were still being understood. The war was over. The atomic age had begun, and the questions occupying the brightest scientific minds of the era were shifting, from the immediate and the urgent toward the vast and the speculative. The conversation that afternoon was light. They were discussing a cartoon that had recently appeared in a New York newspaper, something playful about flying saucers and little green men. The topic drifted, as conversations among scientists tend to do, into broader territory. The men talked about the possibility of extraterrestrial life, about whether other civilizations might exist somewhere out among the stars, about what contact with such a civilization might look like. It was the kind of relaxed, wandering discussion that happens when very intelligent people have a few minutes of unstructured time together. Then, sometime during the meal, one of the physicists at the table, a man named Enrico Fermi, grew quiet for a moment. He seemed to be turning something over in his mind. And then he asked, almost casually, a question that would echo through scientific thinking for the rest of the century and beyond. He asked, "Where is everybody?" It was not an aggressive question. It was not a dramatic one. By all accounts, it was asked with a kind of gentle puzzlement, the way a person might wonder aloud why a friend who was supposed to arrive hours ago has still not appeared. The other men at the table laughed, understanding immediately what he meant, but the simplicity of the question carried an enormous weight, because the more you thought about it, the harder it became to answer. Enrico Fermi was not an ordinary thinker. He was one of the most gifted physicists of the 20th century, a man whose mind moved with unusual ease between theoretical abstraction and practical calculation. He had won the Nobel Prize in Physics in 1938. He had built the world's first nuclear reactor beneath the stands of a football stadium in Chicago in 1942. He was famous among his colleagues for what became known as Fermi estimation, the ability to take a question that seemed impossibly large or complex and break it down into manageable logical pieces until a reasonable answer emerged from what had seemed like impenetrable uncertainty. The classic example of this approach is simple. If someone asked Fermi how many piano tuners worked in Chicago, he would not throw up his hands. He would reason through it quietly. How many people live in Chicago? How many households? What fraction of households might own a piano? How often a piano needs tuning? How long a tuning takes? How many hours a tuner works in a year? And from those estimates, each reasonable on its own, a number would emerge that was almost always surprisingly close to the truth. The method was not magic. It was just careful, patient reasoning applied to big questions. When the first atomic bomb was tested in the New Mexico desert in July of 1945, Fermi dropped small scraps of paper from his hand as the shockwave from the explosion passed over him. He watched how far they traveled and used that distance to estimate the explosion's yield on the spot. His answer was close to what the instruments later confirmed. That was the kind of mind he carried with him everywhere, even to lunch. So when Fermi asked where everybody was, he was not asking idly. He was doing what he always did, looking at what the numbers implied and noticing that something did not add up. The numbers, even in 1950, were suggestive. Our galaxy alone contains somewhere between 100 billion and 400 billion stars. Many of those stars are similar to our Sun in size, temperature, and stability. Many of them are far older than our Sun, which itself formed roughly 4.5 billion years ago in a galaxy that had already been producing stars for billions of years before that. The Milky Way is ancient. Its oldest stars have been burning for nearly as long as the universe has existed. If even a small fraction of those older stars hosted planets, and if even a small fraction of those planets developed conditions suitable for life, and if even a small fraction of the life that emerged eventually developed intelligence and technology, then some of those civilizations would have had enormous head starts on humanity. Not thousands of years ahead of us, not millions, billions. Billions of years in which to develop, to spread, to build things on scales we can barely imagine, to send signals across the galaxy, to leave some kind of mark on the cosmos that a young and curious civilization like ours might eventually detect. And yet we had detected nothing. No signals, no visitors, no structures visible against the stars, no radio transmissions crossing the void, no artifacts drifting through our solar system, no evidence of any kind that anyone else had ever existed out there among the hundreds of billions of stars that filled the sky above New Mexico that summer. Fermi's question was simple, but it pointed at something genuinely strange. The universe appeared on the face of it to be exactly the kind of place where life should be abundant. The ingredients for chemistry are everywhere. Stars are everywhere. Time is everywhere. And yet everything we could observe suggested that we were completely, profoundly, and perhaps permanently alone. This tension between what the mathematics of probability suggested should be the case and what our observations actually showed became known in the years and decades that followed as the Fermi Paradox. It is not a paradox in the strict logical sense, the kind where two demonstrably true statements flatly contradict each other and cannot both be right. It is something softer than that, but in some ways more unsettling. It is a gap, a persistent yawning gap between expectation and reality that has resisted every attempt to close it cleanly or comfortably. In the decades since that lunch in New Mexico, some of the finest scientific minds on Earth have taken Fermi's question seriously and turned the full weight of modern astronomy and biology and mathematics toward it. They have built radio telescopes and pointed them at thousands of stars, listening for patterns in the noise. They have developed formal mathematical frameworks for estimating the probability of intelligent life in the galaxy. They have proposed explanations for the silence that range from the quietly sobering to the genuinely strange. They have argued about what counts as evidence, about what we should expect to detect, about whether our search methods are even capable of finding what we are looking for. And none of them, not a single one, has been able to answer the question definitively. Where is everybody? It is worth pausing here, in the early part of this exploration, to appreciate how unusual that is. Science has answered questions that once seemed completely beyond human understanding. We know how stars are born and how they die. We know the age of the universe to within a small margin of error. We have mapped the structure of DNA and landed instruments on other planets and detected gravitational waves produced by colliding black holes a billion light-years away. Science, when given enough time and enough careful effort, tends to find answers. The Fermi Paradox has resisted, not because scientists have not tried, but because the question touches something genuinely difficult: the origin and prevalence of life itself, the nature of intelligence, the long-term trajectory of civilizations, and the fundamental limits of what we can detect across the staggering distances of space. These are not easy problems. They sit at the edge of what we currently know and reach into territory where our knowledge becomes thin and uncertain. Tonight, we are going to explore that territory slowly and without alarm. We are going to look at the paradox from multiple angles, consider the explanations that have been offered, and think carefully about what the silence might and might not mean. Not to frighten or to unsettle, not to suggest that the universe is a dark or dangerous place, but to understand, as best we can, the strange and remarkable situation we find ourselves in. Alive, aware, curious, on a small planet orbiting an ordinary star in one of hundreds of billions of galaxies, listening to a universe that has so far said nothing back. Fermi himself did not spend much time on the question after that lunch. He moved on to other problems, as brilliant minds tend to do. He died 4 years later, in 1954, at the age of 53. But the question he left behind has proven remarkably durable. It has grown, over the decades, into one of the most genuinely fascinating puzzles in all of science. It sits at the intersection of astronomy and biology and physics and philosophy. It touches something ancient in the human experience, the quiet, persistent longing to know whether we are truly alone in the dark. Chapter 2. The Drake Equation. In the years following Fermi's lunch table observation, his question floated through the scientific community without a formal home. It was the kind of question that serious researchers found genuinely interesting, but had no established framework for approaching. It lived in the margins of conversations, in the footnotes of papers about radio astronomy, in the speculative corners of late-night discussions among scientists who found themselves drawn to its implications but unsure how to treat it rigorously. That began to change in November of 1961, 11 years after Fermi's casual remark, when a young astronomer named Frank Drake organized a small and somewhat unconventional meeting at the National Radio Astronomy Observatory in Greenbank, West Virginia. The meeting brought together a handful of scientists from different disciplines: astronomers, physicists, biologists, chemists, to think seriously and collectively about the question of intelligent life beyond Earth. It was one of the first times that question had been treated as a legitimate subject of scientific inquiry rather than science fiction. To prepare for the meeting, Drake did what scientists do when confronting a large and unwieldy problem. He tried to organize it. He sat down and thought carefully about all the factors that would need to be true simultaneously for another technological civilization to exist in our galaxy and to be detectable by us. And he arranged those factors into a simple equation, not because he believed the equation could be solved with any precision, but because it could serve as a framework, a way of making sure that everyone in the room was thinking about the same components of the same problem. The equation Drake wrote on the blackboard that morning in Green Bank is still discussed today. It is known simply as the Drake equation, and while its individual terms remain deeply uncertain, its structure has proven remarkably useful as a way of organizing thinking about the Fermi Paradox. The equation begins with the rate at which new stars form in our galaxy. This is perhaps the most well-constrained term in the entire equation. Astronomers have studied star formation extensively and have reasonably good estimates for how many new stars the Milky Way produces each year. The number is somewhere in the range of 1 to 3 new stars per year, a rate that has been more or less consistent over much of the galaxy's history. This first term is solid ground. From there, the equation moves to the fraction of those stars that have planetary systems. In Drake's time, this was almost entirely unknown. No confirmed exoplanet had yet been detected around another star. The existence of planets beyond our solar system was assumed by many astronomers, but had not been directly observed. Drake and his colleagues could only guess. Their guesses turned out, in retrospect, to be roughly correct, but they had no way of knowing that at the time. Today, thanks largely to missions like the Kepler Space Telescope and the work of thousands of astronomers over the past 3 decades, we have a much clearer picture. Planets are not rare. They are extraordinarily common. Most stars appear to host at least one planet, and many host several. The Milky Way likely contains hundreds of billions of planets in total. This second term, which once seemed deeply uncertain, has turned out to be reassuringly large. The equation then asks what fraction of those planets might be capable of supporting life. The so-called habitable zone planets, those orbiting at a distance from their star where liquid water could exist on the surface. Again, early estimates were guesswork. Today we know that habitable zone planets are also quite common. Billions of them exist in our galaxy alone. The number continues to grow as our detection methods improve. And here is where the Drake equation begins to move from the relatively firm ground of astronomy into the much softer territory of biology and beyond. The next term asks what fraction of habitable planets actually develop life. This is a question that current science cannot answer with any confidence. We have exactly one data point: Earth. Life arose on our planet remarkably quickly in geological terms, within a few 100 million years of the surface cooling enough to support it. Some scientists take this as a hint that life may emerge readily wherever conditions allow. Others argue that the origin of life was an extraordinarily improbable chemical accident that might happen only once in billions of planetary histories. Both positions are defensible. Neither can currently be confirmed or ruled out. From life, the equation moves to intelligence. What fraction of life-bearing worlds eventually produce organisms capable of complex thought, communication, and technology? Here again, Earth offers only a single example. Intelligence evolved on our planet, but it took roughly 4 billion years of biological evolution to get there. And for most of that time, the dominant forms of life were single-celled organisms with no nervous systems at all. Intelligence is not inevitable. It may be common. It may be vanishingly rare. We genuinely do not know. The equation then considers what fraction of intelligent civilizations develop the kind of technology that would make them detectable across interstellar distances. Specifically, technology that produces signals or structures visible from far away. This too is uncertain. A civilization might be intelligent and sophisticated without ever developing radio technology. It might develop technology and then choose not to broadcast. It might develop technology and then disappear before sending anything outward. The final term in the Drake equation is perhaps the most haunting. It asks how long, on average, a technological civilization survives and continues to be detectable. This is the term that carries the most weight in determining whether the galaxy should be full of signals or quiet. If civilizations typically survive for millions of years and continue broadcasting throughout that time, the galaxy should be alive with transmission. If civilizations typically last only a few thousand years before going silent, through war, environmental collapse, or simply choosing to stop broadcasting, then the galaxy might be full of dead or dormant civilizations whose signals have long since faded. When Drake and his colleagues ran through the equation at Green Bank in 1961, using their best estimates for each term, they arrived at a number somewhere in the thousands. Thousands of detectable civilizations potentially existing in the Milky Way at any given time. It was an encouraging result, or at least an interesting one. It suggested that the search for extraterrestrial intelligence was not obviously hopeless. But the equation's real value was never in the specific number it produced. Its value was in making explicit just how many independent conditions had to be satisfied simultaneously for another civilization to exist and be detectable. Each term is a filter. Each term reduces the number of potential civilizations from the vast number of stars we start with. And if even one of those terms is very small, if life is extremely rare, or intelligence is extremely rare, or civilizations are extremely short-lived, then the final number could easily be 1, or 0, or a decimal fraction suggesting that we might be the only technological civilization our galaxy has ever produced. Drake himself remained optimistic throughout his life. He believed the equation's terms were likely favorable, and that the galaxy probably harbored many civilizations. He died in 2022, having spent more than 6 decades thinking about the problem he helped formalize, without ever receiving confirmation that anyone else was out there. The equation he wrote on that blackboard in West Virginia is still with us. It has been refined, debated, and updated many times over the decades. New terms have been proposed. Old terms have been reinterpreted, but its fundamental structure remains the same. A quiet, patient invitation to think carefully about what it takes for life to arise, to develop intelligence, to reach outward, and to last long enough to be found. It does not answer the Fermi Paradox. Nothing so far has done that, but it gives us a language for discussing it, a set of handles on a question that might otherwise feel too large and too strange to hold. Chapter 3. The Scale of Cosmic Time. There is a particular kind of difficulty that arises when human beings try to think about very large numbers. We are reasonably comfortable with the scale of a human life. We can feel the weight of a century, can imagine the span of a few generations, can picture the arc of recorded history stretching back a few thousand years to the first cities and the first written languages. But when numbers grow beyond that, when they reach into the millions and billions, something in our intuition quietly gives up. The numbers become symbols rather than felt realities. We say 13.8 billion years and nod, but we do not truly feel what that means. Tonight it is worth trying. because the Fermi Paradox cannot be fully appreciated without some genuine sense of cosmic time. The silence of the universe looks very different depending on how clearly you understand the timescales involved. The universe is approximately 13.8 billion years old. That number is the result of decades of careful measurement, of the cosmic microwave background radiation, of the expansion rate of the universe, of the ages of the oldest stars we can observe. It is not a guess. It is one of the most well-established figures in all of modern cosmology. To get some feel for what 13.8 billion years actually means, consider an analogy that the astronomer Carl Sagan helped popularize. Imagine compressing the entire history of the universe into a single calendar year. Every month represents a little over 1 billion years. Every day represents roughly 38 million years. Every second represents around 440 years. On this cosmic calendar, the Big Bang happens at the very first moment of January 1st. The first stars ignite sometime in January. Our own Milky Way galaxy begins to form in March. Our sun does not appear until early September. The solar system is, in cosmic terms, a relatively recent development. Earth forms shortly after, also in September. The first simple life appears on Earth in late September or early October. For the next 2.5 months of the cosmic calendar, life on Earth remains microscopic and largely invisible. Single-celled organisms drifting through ancient oceans, slowly and quietly diversifying. The first complex multicellular animals do not appear until mid-November. The dinosaurs arrive in mid-December and are gone by the day after Christmas. Our own species, Homo sapiens, appears in the final minutes of December 31st. All of recorded human history, every civilization, every war, every scientific discovery, every work of art or literature or music that has ever been created, takes place in the last 10 seconds of the last day of the cosmic year. Sit with that for a moment. 10 seconds. Now consider what this means for the Fermi Paradox. If another civilization arose somewhere in the Milky Way even modestly earlier than we did, say, 1 billion years ago on our regular calendar, which is less than 3 weeks earlier on the cosmic calendar, that civilization would have had 1 billion years of additional time to develop. 1 billion years is longer than the entire history of complex animal life on Earth. It is longer than the time it took our ancestors to evolve from simple worms into human beings. A civilization with that kind of head start, if it survived and continued to develop, would be as far beyond us technologically as we are beyond the bacteria that populated early Earth. This is sometimes called the problem of the old ones, the question of where the ancient civilizations are. Not civilizations a few thousand years more advanced than us, or even a few million years more advanced, but civilizations that arose when the galaxy was young and have been developing ever since. If even one such civilization existed and chose to expand, it could theoretically have spread across the entire Milky Way in a time frame that is short by cosmic standards. Estimates vary, but even with relatively slow interstellar travel, a small fraction of the speed of light, a sufficiently motivated civilization could colonize the entire galaxy in somewhere between 10 million and 100 million years. 100 million years sounds enormous, but on the cosmic calendar, it is less than 3 days. The galaxy has had billions of years available for this kind of expansion to happen, and yet there is no evidence that it has. This is one of the sharpest edges of the Fermi Paradox. It is not just that we have not received a radio signal from another civilization. It is that we see no evidence of any large-scale engineering in our galaxy. No signs of stellar energy harvesting on a massive scale. No unusual patterns in the light curves of distant stars that suggest artificial structures. No anomalies in the distribution of matter that would indicate deliberate rearrangement over vast areas. The galaxy, as best we can observe it, looks natural, unmodified, untouched. A universe in which ancient civilizations are common should probably not look like that. There is another dimension of cosmic time worth considering here, and it has to do not with the age of the universe, but with its structure at different moments in its history. The universe has not always been the same kind of place. In its earliest billions of years, it was a more turbulent and hostile environment. Gamma-ray bursts were more frequent. Heavy elements, the carbon, oxygen, nitrogen, and iron that complex chemistry and biology depend on, were less abundant because they are forged inside stars and distributed through supernova explosions, a process that takes time. The first generations of stars were made almost entirely of hydrogen and helium. It was only through successive cycles of stellar birth and death that the heavier elements necessary for rocky planets and organic molecules became widespread. This means that the universe had to reach a certain age before it could support the kind of chemistry that life as we know it requires. Astronomers sometimes refer to this as the question of cosmic habitability, not just whether individual planets are habitable, but whether the universe itself is in a state that permits complex life to exist. By most estimates, the universe became genuinely hospitable to life somewhere around 8 to 10 billion years ago, when enough heavy elements had been distributed through the galaxy to allow rocky planets to form in substantial numbers. Our own solar system formed near the middle of this habitable window, not at its beginning, which means there have been billions of years during which other solar systems, seeded with the necessary elements, could have produced life and allowed it to develop toward intelligence. Billions of years is a very long time. Long enough, in principle, for civilizations to rise, flourish, spread, and perhaps eventually fall or go quiet. Long enough for the process to have happened many times over, in many places, before our own planet had even cooled enough to hold liquid water on its surface. And yet, here we are, alone, as far as we can tell, listening to a galaxy that has had billions of years to fill with voices and has instead remained quiet. This is not necessarily cause for despair. The timescales involved are so large that they actually offer some comfort. The universe is under no obligation to have arranged itself for our convenience or our detection. Civilizations separated by hundreds of millions of years are not really contemporaries in any meaningful sense. They might as well exist in different universes. The window during which two civilizations would need to overlap in time, in addition to being close enough in space to communicate, is narrow in a way that the raw numbers of stars and planets do not immediately suggest. Time, in other words, is a filter just as surely as distance is. And when you begin to appreciate the true depth of cosmic time, the billions of years that separate us not just from the edges of the universe, but from other moments in the universe's own history, the silence begins to seem a little less strange, not fully explained, not resolved, but perhaps a little more understandable. The universe is old in ways that our minds were not built to grasp, and the Fermi Paradox lives, in large part, inside that gap between what we know intellectually and what we can truly feel. Chapter 4. The Great Filter. Of all the proposed explanations for the silence of the universe, one stands apart from the others, not because it is the most scientifically rigorous, and not because it has the most empirical support, but because of what it implies if it turns out to be correct. It is an idea that has a way of sitting quietly in the back of the mind long after you first encounter it, returning at unexpected moments, asking to be thought about again. It is called the Great Filter. The concept was introduced in 1998 by an economist and philosopher named Robin Hanson in an essay that approached the Fermi Paradox from an unusual angle. Hanson was not primarily an astronomer or a biologist. He was a thinker interested in probability and in the long-term trajectory of intelligent life. And the question he asked was essentially this: if the universe is as old and as vast as we know it to be, and if the ingredients for life are as widespread as they appear, then something must be preventing the galaxy from filling up with observable civilizations. Something, somewhere along the path from simple chemistry to galaxy-spanning intelligence, must be extremely difficult to cross. A barrier, a bottleneck, a step so hard that almost no one makes it through. Hansen called this barrier the Great Filter. The logic is straightforward. Start with the hundreds of billions of stars in our galaxy. Assume that a reasonable fraction of them host rocky planets in habitable zones. The numbers are large enough that even with conservative estimates, you would expect intelligent life to be widespread, unless something is stopping it. The Great Filter is whatever that something is. It is the step, or perhaps the collection of steps, that reduces the vast number of potentially life-bearing worlds down to the small number of civilizations that actually survive and become visible. The critical question, the one that gives the Great Filter its particular weight, is not whether the filter exists. Given the silence of the universe, most serious thinkers on this subject accept that something is filtering the population of potential civilizations down to something very small, possibly zero. The critical question is where the filter is located in time. Is it behind us, or is it ahead of us? If the Great Filter is behind us, if it is something that our planet and our lineage already navigated successfully somewhere in the deep past, then we are in a relatively fortunate position. We made it through. Whatever the hard step was, we crossed it. The silence of the universe is explained by the fact that the filter is genuinely difficult, that most worlds never get past it, and that we happen to be among the rare exceptions. If the Great Filter is ahead of us, if it is something that no civilization has yet successfully crossed, a challenge that destroys or silences every technological species before it can become truly visible on a galactic scale, then the silence of the universe carries a very different meaning. It means that something is coming, something that has stopped every civilization before us and that we have not yet encountered. These two possibilities sit at the heart of much of the thinking around the Fermi Paradox, and the question of which is more likely depends heavily on what we discover about life and intelligence elsewhere in the universe. Consider the first possibility. What might a behind-us Great Filter look like? There are several candidates that scientists and philosophers have proposed over the years. One of the most discussed is the origin of life itself, the step from complex chemistry to a self-replicating molecule. The first true ancestor of all living things may be extraordinarily improbable. We know it happened on Earth, but we have no way of knowing how often it happens elsewhere. If the emergence of life from non-living chemistry requires a specific and unlikely sequence of chemical events, something that might occur only once in billions of planetary histories, then the filter could be right there at the very beginning. Most worlds, in this scenario, never produce life at all. They remain chemically rich, but biologically empty for their entire existence. Another candidate for a behind-us filter is the transition from simple single-celled life to complex eukaryotic cells. Cells with a nucleus and internal structures that allow for much greater biological complexity. This transition happened only once in Earth's history, roughly 2 billion years ago, and it appears to have been a genuinely difficult and unlikely event. For the first 2 billion years of life on Earth, nothing more complex than simple bacteria existed. The jump to complex cellular architecture may have been another narrow bottleneck, one that many otherwise life-bearing worlds never successfully navigate. The emergence of multicellular organisms, the development of sexual reproduction, the appearance of nervous systems, the evolution of intelligence itself. Each of these transitions could, in principle, represent a filter. Each of them happened on Earth, but each of them took an enormous amount of time and may have required specific conditions that are not commonly reproduced elsewhere. If any one of these transitions is genuinely rare, rare enough that it happens on only a tiny fraction of life-bearing worlds, then the great filter is behind us, and the silence of the universe makes sense without requiring anything alarming about the future. This would be, in a quiet way, good news. Now consider the second possibility. What might an ahead-of-us great filter look like? Here, the imagination is drawn toward things that technological civilizations might do to themselves or encounter as they develop. Nuclear war is the most obvious candidate, given that our own civilization came uncomfortably close to it during the 20th century. Environmental collapse is another. The possibility that industrial civilizations inevitably alter their planetary conditions in ways that become unsustainable before they develop the technology to escape or compensate. Engineered biological catastrophes, artificial intelligence that develops in ways destructive to its creators, resource depletion on a civilizational scale. All of these have been proposed as potential ahead-of-us filters. There is also a category of filter that involves not destruction, but transformation or withdrawal. Some thinkers have proposed that civilizations reaching a certain level of technological sophistication tend to turn inward, retreating into virtual realities or altered states of existence that are absorbing enough to make outward expansion seem pointless. A civilization that has solved the problem of subjective experience and can generate any desired internal reality might simply stop broadcasting, stop expanding, and become invisible to outside observers. This is sometimes called the transcension hypothesis, and it offers a filter that is less catastrophic but equally effective at explaining the silence. The discovery of life elsewhere in the universe, even simple microbial life on Mars or in the oceans of Europa, would have significant implications for how we think about the filter's location. If life arose independently on another world in our own solar system, that would suggest that the origin of life is not particularly rare. It would mean that the early steps of the biological journey are relatively easy to take. And if those early steps are easy, then the filter must be somewhere further along the path, somewhere that we have not yet reached. This is why some scientists describe the potential discovery of microbial life elsewhere in our solar system as both one of the most exciting and one of the most sobering possible scientific findings. Exciting because it would confirm that life is not unique to Earth. Sobering because it would push the great filter forward in time, making it more likely that the hard step lies somewhere ahead of us rather than behind us. Robin Hanson himself has written about this tension with characteristic directness. The better the news seems on the surface, life is common, intelligence arises readily, civilizations form without great difficulty, the worse the implied news about the filter's location becomes. If everything up to our current state is easy, then something very hard must be coming. It is worth being clear about what the great filter concept is and is not. It is not a prediction. It is not a theory with strong empirical support in the traditional scientific sense. It is a logical framework, a way of thinking about what the silence of the universe implies, given what we know about the age and size of the cosmos and the apparent absence of other civilizations within it. And it is a framework that rewards sitting with, because it sharpens the questions we should be asking. When we look for life on other worlds, we are not just satisfying curiosity, we are gathering evidence about where the filter lies. When we think about the long-term stability of our own civilization, we are not just engaging in practical risk management. We are thinking about whether we are the first species to approach whatever lies ahead, or whether we are walking a path that others have already walked and not returned from. These are large and serious thoughts. They are also, ultimately, hopeful ones, because the fact that we are here asking these questions means that we have made it this far. Whatever filters existed in our past, we passed through them. That is not nothing. In a universe that may be littered with worlds where life never quite got started, or never quite crossed the threshold to complexity, or never quite made it to the point of looking upward and wondering, the simple fact of our existence and our curiosity is something worth noticing. The great filter reminds us that being here, aware and wondering, is not guaranteed. It may be rare. It may be precious in ways that are difficult to fully articulate. Chapter 5. The Rare Earth Hypothesis. There is a particular assumption that runs quietly through a great deal of thinking about the Fermi Paradox, an assumption so intuitive that it often goes unexamined. It is the assumption that Earth is ordinary, that our planet is a fairly typical example of a rocky world in a habitable zone, that the conditions which allowed life to emerge and flourish here are not especially unusual, and that the universe is therefore likely full of similar worlds producing similar results. This assumption has a name in science. It is called the Copernican principle, or sometimes the principle of mediocrity. It traces its philosophical roots to Nicholas Copernicus, who demonstrated in the 16th century that Earth is not the center of the solar system. That insight was extended over the centuries that followed into a broader philosophical stance, that Earth is not special, that our sun is not special, that our position in the galaxy is not special, and that life on Earth is probably not special either. We are, on this view, one unremarkable example among countless similar examples scattered throughout the cosmos. It is a useful and important corrective to human self-importance, and it has served science well in many contexts. But two scientists, a paleontologist named Peter Ward and an astronomer named Joe Brownlee, published a book in the year 2000 that challenged this assumption directly and carefully. The book was called Rare Earth, and its central argument was that the conditions necessary for complex life, not just microbial life, but the kind of multicellular, biologically sophisticated life that eventually gives rise to intelligence, are far more specific and far less common than the principle of mediocrity would suggest. Their argument was not that life is impossible elsewhere. It was that complex life requires an extraordinary and unlikely combination of circumstances, and that Earth happens to sit at the intersection of many of those circumstances simultaneously. Remove any one of them, and the history of life on this planet might have gone very differently. The first, and perhaps most fundamental of these circumstances, is the location of our solar system within the Milky Way. Our Sun orbits the galactic center at a distance of roughly 26,000 light-years, placing us in a region sometimes called the galactic habitable zone. This is not the center of the galaxy, where stellar density is high and radiation from the central black hole and nearby supernova would make the environment hostile to complex life. And it is not the outer edge of the galaxy, where heavy elements, the building blocks of rocky planets and organic chemistry, are less abundant because fewer generations of stars have lived and died there. We sit in a relatively calm, well-supplied middle region of the galaxy, far enough from dangerous environments to be stable, close enough to the galactic center to be rich in the elements that life requires. This positioning is not guaranteed. Many stars in the Milky Way orbit in less hospitable regions. The galactic habitable zone, by some estimates, contains only a fraction of the galaxy's total stellar population. Consider next the nature of our Sun. It is a G-type main sequence star, what astronomers sometimes call a yellow dwarf, though its light is more accurately described as white. It is medium-sized, stable, and long-lived. It has been burning at a relatively consistent rate for 4.5 billion years and will continue to do so for roughly another 5 billion years. This stability matters enormously for life. Complex biological evolution takes time, vast amounts of it. The journey from single-celled organisms to multicellular life to intelligence required billions of years of relatively stable conditions on Earth. A star that varies significantly in its energy output, or that produces frequent intense flares, or that burns through its fuel too quickly, might not allow enough time for that journey to complete. Many stars in the galaxy are not like our Sun. Red dwarf stars, which are the most common type, are smaller, cooler, and often highly active in their early years, producing radiation that could strip away planetary atmospheres and sterilize surfaces. Whether complex life can develop around red dwarfs is still an open question, but the conditions are certainly different from those our own planet has enjoyed. Then there is the matter of Jupiter. Our solar system's largest planet sits far from the Sun, in the cold outer regions of the solar system, and its enormous gravitational influence has had a profound effect on Earth's history. Jupiter acts, in a sense, as a shield. Its gravity captures or deflects a significant fraction of the comets and asteroids that might otherwise strike the inner solar system with much greater frequency. Without Jupiter, Earth would likely have been bombarded far more heavily throughout its history, making the development of complex life significantly more difficult. Some astronomers have called Jupiter Earth's guardian, and while the relationship is more complicated than that simple description suggests, the basic principle holds. A solar system without a large outer planet in the right location might be a much more violent and unstable environment for inner rocky planets. Our moon deserves attention here as well. Earth's moon is unusually large relative to its host planet. No other rocky planet in our solar system has a moon of comparable proportional size. This large moon has had two important effects on Earth's development as a habitat for life. First, it stabilizes the tilt of Earth's rotational axis. Without the moon's gravitational steadying influence, Earth's axial tilt might vary chaotically over millions of years, producing wild swings in climate that could be catastrophic for complex ecosystems. Second, the moon's tidal forces have played a role in driving geological and possibly biological processes over the history of life on Earth. The origin of our large moon is itself an unlikely story. It appears to be the result of a giant impact between early Earth and a Mars-sized body early in the solar system's history, an event that could easily not have happened, or could have happened differently. Plate tectonics, the slow movement of Earth's crustal plates over the mantle beneath, is another factor that Ward and Brownlee identified as potentially critical to complex life. Earth's tectonic activity drives a long-term carbon cycle that helps regulate the planet's temperature over geological timescales, acting as a kind of planetary thermostat. It recycles nutrients from the deep interior of the planet to the surface. It drives the geological activity that maintains Earth's magnetic field, which in turn shields the surface from harmful solar radiation. Not all rocky planets have active plate tectonics. Mars appears to have had it once and lost it. Venus, despite being similar to Earth in size and composition, does not have it in the same form. Whether plate tectonics is a necessary condition for complex life, or merely a helpful one, is still debated. But its absence would likely make Earth a significantly less hospitable place. And then there is the simple matter of time and stability. Earth has existed in a relatively stable state, with liquid water on its surface, for most of its 4.5 billion year history. There have been disruptions, mass extinctions, ice ages, periods of intense volcanic activity. But the planet has not been rendered permanently uninhabitable. Life has persisted through every catastrophe it has faced and has continued to diversify and complexify. This persistence required not just the right initial conditions, but their maintenance over a time frame that challenges imagination. The rare Earth hypothesis does not claim that Earth is the only world where complex life exists. It claims that the combination of factors that made complex life possible here is unusual enough that such worlds might be genuinely scarce across the galaxy. Simple microbial life, hardy, adaptable, requiring far less in the way of specific conditions, might be common. Bacteria have proven themselves capable of surviving in environments that would be instantly lethal to complex animals. If life emerges wherever the basic chemical conditions allow, then the universe might be rich with microbes, while remaining largely empty of anything more elaborate. This distinction matters for the Fermi Paradox, because the paradox is specifically about intelligent, technological civilizations, the kind that build radio telescopes and send signals and leave evidence of their existence that other civilizations might detect. If the path from simple life to complex life to intelligence requires the rare alignment of galactic position, stellar type, planetary companions, geological activity, lunar stabilization, and billions of years of uninterrupted stability, then the number of worlds that have actually produced technological civilizations might be very small indeed. It might, in fact, be one. The rare Earth hypothesis is not universally accepted. Many scientists find it too Earth-centric, too focused on the specific pathway that life took on our planet, too quick to generalize from a single example. Life might find ways to achieve complexity through routes we have not imagined, under conditions we would not have predicted. The history of biology is full of surprises. The history of planetary science is full of worlds that turned out to be more interesting than expected. But the hypothesis does something valuable regardless of whether its conclusions are correct. It forces a careful examination of the assumptions we bring to the question of life in the universe. It asks us to look honestly at how many things had to go right for us to be here, and to consider seriously the possibility that not all of those things go right everywhere. Earth, on this view, is not a typical planet. It is an extraordinarily fortunate one, and the silence of the universe might simply be the sound of that fortune being rare. Chapter 6. Other proposed solutions. The Great Filter and the Rare Earth hypothesis represent two of the most thoroughly developed responses to the Fermi Paradox, but they are not the only ones. Over the decades since Fermi's lunch table, question entered serious scientific discourse. Researchers and thinkers from a wide range of disciplines have proposed other explanations for the silence, some grounded in observational astronomy, some in theoretical physics, some in sociology and philosophy, and some in territory that sits at the edges of conventional scientific thinking. None of these proposals has been confirmed. None has been ruled out. They exist as a collection of possibilities, each illuminating a different aspect of the problem, each asking us to consider the universe from a slightly different angle. Tonight, we will move through several of them slowly, giving each one the space it deserves. The first is known as the zoo hypothesis. The zoo hypothesis was proposed in 1973 by the astronomer John Ball, and its central idea is disarmingly simple. Perhaps we have not detected other civilizations, not because they do not exist, but because they have chosen not to make themselves known to us. Perhaps advanced civilizations are aware of our existence and have collectively decided, for reasons of their own, to observe without interfering, to watch us from a careful distance, the way a wildlife biologist might observe an animal in its natural habitat without disturbing it. The name comes from the analogy of a zoo or a nature reserve, where the animals within live their lives without awareness of the humans observing them from outside. On this view, Earth is something like a protected habitat, and humanity is something like a species under quiet observation by intelligences that have the capability to contact us but have chosen restraint. The hypothesis has a certain intuitive appeal. It offers a benign explanation for the silence, not absence, but deliberate non-interference. It also raises interesting questions about what the conditions for such interference might be. Perhaps advanced civilizations have agreed on something like a non-contact protocol, a galactic norm of not disrupting younger civilizations before they reach a certain level of development. Perhaps first contact, in this framework, is something that happens only when a civilization demonstrates it is ready, whatever ready might mean. The zoo hypothesis is difficult to evaluate scientifically, which is both its weakness and a genuine feature of the problem it addresses. It is hard to design an observation or experiment that would distinguish between a universe containing no other civilizations and a universe containing many civilizations that have all agreed to stay quiet. The hypothesis asks us to consider absence of evidence as potentially consistent with the presence of observers, a frustrating position for scientific inquiry, which generally prefers testable predictions. A darker proposal is known as the dark forest theory. The dark forest theory takes its name from a metaphor developed by the Chinese science fiction author Liu Cixin in his celebrated trilogy, though the underlying logic had been explored by others before him. The theory begins with two premises. First, that all civilizations require resources to survive and grow, and that resources in the universe are ultimately finite. Second, that it is impossible for any civilization to be certain of the intentions of another civilization it encounters, and that the cost of being wrong about those intentions, of assuming friendliness and being met with hostility, could be annihilation. Given these premises, the theory argues that the rational strategy for any sufficiently advanced civilization is silence and concealment. Broadcasting your existence in a universe where other civilizations might view you as a competitor or a threat is an act of profound risk. The civilizations that survive on this view are the ones that go dark, that eliminate any signal of their existence and strike preemptively at any civilization they detect before that civilization can become a threat. The universe, in this framework, is a dark forest in which every hunter moves silently, knowing that any sound they make might bring something dangerous toward them. The dark forest theory is deeply unsettling in its implications, and it is worth being clear that it is a speculative philosophical argument rather than a scientific theory with empirical support. It assumes a particular model of how advanced civilizations would reason and behave, a model grounded in scarcity and fear. Many thinkers have challenged these assumptions, arguing that sufficiently advanced civilizations might find ways to transcend resource competition, or that cooperation might prove more evolutionarily stable than predation at civilizational scales. The theory tells us more about certain human anxieties than it necessarily tells us about the universe, but it cannot be entirely dismissed. The logic is internally consistent, and the silence it predicts matches what we observe. If the dark forest is real, we would expect to see exactly what we see: a quiet sky and no evidence of anyone out there. A more gentle and philosophically rich proposal is sometimes called the transcension hypothesis, developed most fully by the futurist John Smart. The transcension hypothesis suggests that the natural developmental trajectory of sufficiently advanced civilizations is not outward expansion across space, but inward exploration, a progressive turn toward greater complexity, intelligence, and density of experience in ever smaller physical and computational spaces. On this view, civilizations do not spread across galaxies, because spreading across galaxies is not what intelligence ultimately does when it matures. Instead, advanced civilizations turn their attention and their technology toward the inner universe, toward the development of increasingly rich and dense information processing, toward what Smart describes as inner space rather than outer space. They become, in a sense, invisible to civilizations still in the outward expansion phase, not because they are hiding, but because they have moved into a domain of existence that produces no signals detectable by radio telescopes or optical observations. The transcension hypothesis is speculative, and it rests on assumptions about the long-term direction of technological development that may or may not prove correct. But it offers something that many other proposed solutions do not: a reason for the silence that doesn't require catastrophe, extinction, or deliberate concealment. It suggests that the silence might be the natural sound of maturity, of civilizations that have found something more interesting to do than announce themselves to the cosmos. Another class of proposed solutions focuses not on the behavior of civilizations, but on the limitations of our search methods. We have been listening for radio signals for a little over 60 years, using telescopes that can survey only a small fraction of the sky at any given time, tuned to a relatively narrow range of frequencies, operating with detection thresholds that might miss all but the most powerful transmissions. The universe is 13.8 billion years old. Our search has lasted less than a human lifetime. This argument does not explain the paradox so much as it contextualizes it. It suggests that our null result, our failure to detect anything, is not yet statistically meaningful. We have not searched thoroughly enough, broadly enough, or for long enough to conclude that nothing is there. The silence we have observed might be the silence of a search that has barely begun. Related to this is the question of whether we are listening for the right things. Our search has been guided by assumptions about what an advanced civilization's signals would look like, assumptions based on our own technology and our own communication methods. But a civilization millions of years more advanced than us might communicate in ways we cannot detect or recognize, using physics we do not yet understand, through channels that do not resemble radio waves at all. The universe might be full of conversation conducted in a language we have not yet learned to hear. The planetarium hypothesis, proposed by the philosopher Stephen Webb, offers a more unsettling variation on this theme. It suggests that what we perceive as the universe, the stars, the galaxies, the vast and ancient cosmos we observe, might be a constructed simulation or illusion, designed by an advanced civilization to give younger species the impression of a vast, empty universe while concealing the true nature of reality behind it. This idea overlaps significantly with broader simulation hypotheses that have been discussed extensively in philosophy and physics, and it is, by its nature, almost impossible to evaluate empirically. But it represents the logical endpoint of a certain line of thinking about the gap between what we observe and what might actually be the case. Finally, there is the possibility that the silence is simply the result of timing. The universe is old, but it hasn't always been hospitable to complex life. As we discussed in our exploration of cosmic time, the conditions for biology as we know it only became widespread a few billion years ago. It is possible that we are among the first technological civilizations to arise in our galaxy, not because we are uniquely special, but because the universe has only recently reached the stage of its development where civilizations like ours are possible at all. Others may be coming, scattered across a future that stretches far beyond anything we can currently observe or imagine. If this is the case, then the silence is not a sign of rarity or catastrophe. It is a sign of earliness. We are not the only ones who will ever look up and wonder. We are simply among the first. That thought, if you let it settle, has a particular quality to it. Not lonely exactly, but alone in the way that anyone is alone who arrives somewhere before the others and waits and watches the horizon. Chapter 7. What the silence might simply mean. There is a temptation, when sitting with the Fermi Paradox long enough, to reach for the most dramatic explanation available. The silence feels like it should mean something large and significant. It feels like it deserves a correspondingly large and significant answer. And so we find ourselves drawn toward the great filter, toward the dark forest, toward civilizational collapse and cosmic catastrophe, as if only something enormous could account for an emptiness this profound. But there is another possibility that deserves its own careful attention, a quieter possibility, one that does not require extinction or concealment or cosmic horror to explain what we observe. The possibility that the silence is simply what we should expect, given the actual mathematics of the situation. This argument begins with distance. Not distance as an abstract concept, but distance as a genuine, physical, almost incomprehensible barrier to detection. The nearest star to our Sun is Proxima Centauri, a small red dwarf approximately 4.2 light-years away. A light-year is the distance light travels in a full year, moving at roughly 300,000 kilometers per second. 4.2 light-years means that light leaving Proxima Centauri takes 4 years and 2 months to reach us. The fastest spacecraft humanity has ever launched would take tens of thousands of years to cover that distance. And Proxima Centauri is our neighbor. It is the closest possible candidate for a nearby civilization. The Milky Way extends roughly 100,000 light-years from edge to edge. The distances between stars, even in the relatively dense region of the galaxy where we reside, are staggering in a way that resists easy internalization. Now consider what those distances mean for detection. Radio signals, like light, travel at the speed of light. A signal broadcast from a civilization on the other side of the galaxy would take 100,000 years to reach us. If that civilization broadcast its signal 100,000 years ago, we might be receiving it right now. But the civilization that sent it could have changed beyond recognition, gone silent, or ceased to exist entirely in the intervening time. We would be hearing a voice from a civilization that no longer exists in the form that produced it. This is not a theoretical problem. It is a fundamental feature of the universe we live in. Communication across interstellar distances is not like picking up a telephone. It is more like finding a message in a bottle that has been drifting across an ocean for geological ages, sent by someone who has no way of knowing whether anyone will ever find it. The mathematics of detection make the situation even more specific. Consider the fraction of the sky that our radio telescopes have actually surveyed with sufficient sensitivity to detect a signal like our own. Our most powerful deliberate broadcasts, signals we have intentionally aimed at the stars, would not be detectable by our own best radio telescopes from even a few light years away. We have been broadcasting unintentionally for about a century, but the sphere of space our signals have reached is only about 200 light years across. In a galaxy 100,000 light years in diameter, that sphere represents a tiny and insignificant volume. When scientists at the SETI Institute and elsewhere listen for signals, they are examining small patches of sky for limited periods of time at specific frequencies, with sensitivity thresholds that might miss all but the most powerful and deliberately aimed transmissions. The cosmic haystack is enormous. Our search has been, by any honest measure, quite small. This does not mean the search is pointless. Every negative result is still a result. Every patch of sky we examine and find quiet narrows the range of possibilities. But it does mean that concluding the universe is empty based on our search so far is a significant overreach. We have looked carefully at a very small corner of a very large room and found it quiet. The rest of the room remains largely unexplored. There is also the question of what we are listening for. Our search for extraterrestrial intelligence has been guided, almost entirely, by assumptions derived from our own technology. We listen for radio waves because we use radio waves. We look for laser pulses because we use laser pulses. We search for patterns that resemble our own communication methods because those are the patterns we know how to recognize. But a civilization 1 million years more advanced than us would no more communicate by radio than we communicate by banging rocks together. The entire electromagnetic spectrum accessible to our instruments represents only a slice of the possible channels through which information might travel. A sufficiently advanced civilization might have discovered ways of transmitting information through mechanisms we have not yet theorized, using physics we have not yet discovered. We might be surrounded by communication we cannot perceive, the way a person deaf from birth is surrounded by sound. This thought is not merely speculative humility. It reflects something genuine about the relationship between technological development and the methods available for communication. Our own technology has changed dramatically in a single century. Radio broadcasting, which seemed like the obvious medium for interstellar communication to the pioneers of SETI in the 1960s, has largely given way to fiber optic cables and tightly focused digital networks that leak almost no signal into space. A civilization that developed radio and then moved quickly to more efficient, more contained communication methods might have been briefly visible in the radio spectrum and then gone quiet again, not because it ceased to exist, but because it stopped broadcasting in ways we can detect. The concept of cosmic loneliness deserves examination here as well. The Fermi Paradox is sometimes discussed as though the absence of contact is inherently troubling, as though the natural state of an inhabited universe should be one of busy communication and frequent encounter. But this assumption may itself reflect a very human and very recent set of expectations. For most of Earth's history, the continents were separated by oceans that made contact between distant human populations slow and difficult. Civilizations developed in relative isolation from one another for thousands of years. The era of instantaneous global communication is extraordinarily recent. It may be that isolation is simply the default condition of intelligence in a universe this large, and that contact, when it happens, is the exception rather than the rule. There is a version of the Fermi Paradox's resolution that requires no dramatic explanation at all. It requires only that the universe is very large, that life is somewhat rare, that civilizations are not evenly distributed across space and time, that the window during which any given civilization broadcasts in a detectable way is relatively short compared to cosmic timescales, and that our search has been too limited in scope and duration to have found what might be there. Take each of those conditions separately. Each one seems plausible. Combined, they produce a universe that looks exactly like the one we observe. Vast, ancient, and apparently quiet, not because it is empty, but because the distances and timescales and detection challenges are genuinely, almost unimaginably large. This resolution to the paradox does not have a dramatic name. It is sometimes called the rare and faraway hypothesis, or simply the argument from improbability of detection. It lacks the intellectual sharpness of the great filter and the philosophical richness of the transcension hypothesis. But it may be the most honest answer available to us at this stage of our development. We have not found anyone. We have not looked very hard, or very long, or very broadly. The universe is under no obligation to arrange itself so that its inhabitants are easy to find. There is something almost peaceful in this conclusion, if you allow yourself to sit with it. The silence is not a verdict. It is not evidence of catastrophe or rarity or cosmic indifference. It is simply the honest result of a search that has barely begun, conducted by a species that has been pointing instruments at the sky for less than a century, on a planet that formed 4.5 billion years ago in a universe nearly 14 billion years old. We are early. We are limited. We are listening as carefully as we know how with the tools we currently possess. And the universe, vast and patient and indifferent to our timelines, continues to keep its own counsel. The silence, in the end, may simply mean that we have not yet listened long enough, or well enough, or in the right direction to hear what is there. That is not a comfortable answer, but it may be the truest one available. And there is a particular kind of quiet wonder in that, in being a species young enough to still be at the beginning of the search, in looking up at a sky full of stars and knowing that the question is still genuinely open, in understanding that the silence we hear tonight is not the final word, but simply the current state of an inquiry that may take centuries or millennia to resolve. Chapter 8. Reflections on Being Here. There is a question that sits beneath all the mathematics and the hypotheses and the carefully reasoned arguments we have explored tonight. It is not a scientific question exactly. It does not have a testable prediction or a falsifiable component, but it is the question that gives the Fermi Paradox its deepest resonance. The reason it has captured the imagination of scientists and philosophers and ordinary people who simply find themselves lying awake at night, looking at the ceiling and wondering. The question is this: what does it mean that we are here at all? Not here in the sense of existing on a habitable planet, in a stable solar system, in the galactic habitable zone. We have explored those circumstances at length, but here in the deeper sense, aware, curious, capable of asking the question in the first place, able to look outward at a universe of almost incomprehensible scale and age and ask, quietly and seriously, whether anyone else is doing the same thing somewhere out among the stars. That capacity, the capacity for wonder directed outward, for curiosity about things that have no immediate practical value, for the kind of patient, unhurried inquiry that leads a species to build radio telescopes and point them at distant suns and listen carefully to the silence, is not obviously necessary for survival. Evolution does not optimize for cosmic curiosity. It optimizes for reproduction and survival in local environments. And yet here we are, a species that emerged from the same blind processes of natural selection as every other living thing on this planet, and we are spending our evenings thinking about the Fermi Paradox. That is worth noticing. That is, in its own quiet way, remarkable. The astronomer Carl Sagan wrote, near the end of his life, that we are a way for the cosmos to know itself. It is a phrase that has been quoted many times, perhaps because it captures something that resists more precise expression. The universe has been here for nearly 14 billion years. For most of that time, it contained no awareness of itself, no perspective from which its own existence could be observed or contemplated. And then, through a long and improbable series of events, matter organized itself into forms capable of looking back at the whole and asking what it means. Whether or not we are alone in the universe, that happened here, on this planet, among this particular branch of life. And the Fermi Paradox, whatever its ultimate resolution turns out to be, is in large part a meditation on how strange and significant that is. If we are alone, if the rare earth hypothesis is correct, if the great filter lies behind us, if complex life is genuinely scarce across the cosmos, then the implications are both humbling and quietly extraordinary. It would mean that this small planet, orbiting an unremarkable star in the outer regions of one galaxy among hundreds of billions, is the only place in the observable universe where something is currently looking up and wondering. Every question ever asked by a human mind, every piece of music ever composed, every act of love or curiosity or scientific inquiry, all of it concentrated here, in this one fragile, improbable place. That thought does not produce in most people the feeling of loneliness that the word alone might suggest. It produces something closer to a kind of gentle vertigo, a sense of the weight of what exists on this planet being somehow larger than it appeared before. If we are not alone, if the universe contains other civilizations, separated from us by distances and timescales that make contact difficult or impossible, but present nonetheless, then the implications are different, but no less significant. It would mean that life and intelligence are properties of the universe itself, tendencies that emerge wherever conditions allow, expressions of something deep in the nature of matter and energy and time. It would mean that we are part of a community we have never met, scattered across a cosmos too vast for direct encounter, each civilization alone in its own corner of the dark, but not unique in its aloneness. There is a kind of companionship in that too, a different kind, but real. The Fermi Paradox has no resolution tonight. We have explored the mathematics of probability, the Drake equation and its uncertain terms, the staggering depth of cosmic time, the great filter and its unsettling implications, the rare Earth hypothesis, and the extraordinary combination of conditions that produced life here, the zoo hypothesis and the dark forest, and the transcension hypothesis, and the simple argument from the limits of our search. We have moved through each of these ideas slowly and honestly, and at the end of the journey, we find ourselves in the same place we started, uncertain, but more richly uncertain than before. That is not a failure. That is what genuine inquiry looks like, when it encounters a question that is genuinely hard. The search for extraterrestrial intelligence continues. New telescopes are being built. New detection methods are being developed. New generations of scientists are turning their attention to the question with tools and techniques that Enrico Fermi could not have imagined. when he asked his quiet question over lunch in 1950. The James Webb Space Telescope is examining the atmospheres of exoplanets for chemical signatures that might indicate biological processes. Future missions may send instruments into the oceans of Europa or the methane lakes of Titan to look for evidence of life in our own solar system. The search is slow and patient and ongoing. And perhaps most importantly, our understanding of what to look for is expanding. We are beginning to think more carefully about what an advanced civilization's presence in the universe might actually look like, beyond the radio signals we have been listening for. We are developing the concept of technosignatures, any detectable sign of technology, not just communication, the anomalous dimming of a distant star, an unusual distribution of heat radiation from a galaxy, a pattern in the light curve of a solar system that does not match any natural explanation. We are learning to look for the indirect evidence of intelligence the way a detective looks for the signs of a presence that has not announced itself directly. This expanding search reflects something important about where humanity currently stands in its relationship with the cosmos. We are a young species on a cosmic timescale. We have been technologically capable of this kind of inquiry for less than a century. We have been anatomically modern humans for perhaps 300,000 years, and the universe has been here for nearly 14 billion. If there is a civilization out there that has been developing for even a billion years longer than we have, the difference in capability and perspective would be beyond our current ability to imagine. We are, in the most literal sense, just beginning. And there is something genuinely beautiful in that. The universe is not a solved problem. The sky is not a finished painting. The question of whether we are alone in the cosmos is still open, still alive, still waiting for evidence that has not yet arrived. The silence we hear tonight is not a closed door. It is an open question, hanging in the dark above us, patient and immense and full of possibility. There is a practice among some astronomers and cosmologists of going outside on clear nights and simply looking up. Not with instruments, not with a research agenda, just looking, with the knowledge of what is actually out there, the distances, the timescales, the number of stars, the age of the light arriving at the eye from sources that existed long before Earth was formed. It is a practice that tends to produce a particular quality of feeling, not anxiety, not insignificance, something more like a deep and settled wonder, a sense of being genuinely embedded in something vast and old and not fully understood. The Fermi Paradox lives in that feeling. It is the formal, scientific expression of the same impulse that makes a person stand outside on a clear night and look up. The impulse to take seriously the scale of what is out there, to not look away from the strangeness of existence, to ask the question honestly, even knowing that the honest answer might be, I do not know. Enrico Fermi asked his question over lunch in the summer of 1950 and then moved on to other problems. But the question itself did not move on. It has been living in the minds of scientists and philosophers and curious people ever since, growing slowly larger and more nuanced as our understanding of the universe has deepened. Tonight, we have sat with it together, moved through its dimensions slowly, considered its implications from multiple angles, and arrived not at an answer, but at a richer appreciation of the question itself. The universe is very old. Space is very large. Life, as best we can tell, is rare enough that we have not yet found evidence of it anywhere but here. And here, on this particular planet, around this particular star, in this particular corner of one galaxy among hundreds of billions, something happened that may or may not be common elsewhere. Something became aware of itself. Something looked outward. Something asked where everybody was, and the asking itself, whatever the answer turns out to be, is one of the most extraordinary things that has ever happened in the known universe. Get some rest. The question will still be here tomorrow. And so, remarkably, will we.